I got this random little thing for Christmas. It's like a scented wax melt heater. Little bowl comes off, put some wax cubes in it. Quite like it. It's like cast china with a pattern on it. What I like about it is, good old manual focus, here we go. The bulbs it uses are these good old tungsten filament style bulbs, but you can see the filament in them is ever so flimsy and they do not last long, especially at turn on where current inrush causes localized heating to just make them blow. So I brought a box of like 20 of them, but I'd rather not just get through them every 30 seconds. So I figured, well, I have the means necessary to do something about that. I went and rummaged around, found this nice little die-cast box. It's not particularly small, could ideally do being a little bit smaller, but it'll do. So I'm thinking a zero crossing detector, ramp generator, a TRIAC, and a slower ramp generator running a comparator to fire the TRIAC, and yeah, give it so like it gives it like 100 crossings or something over the course of a second before it actually switches to full mains voltage across the bulb. At least it'll prevent those annoying turn-on spikes from blowing the bulb. They still won't last overly long because, like I say, they're tiny little things. So we'll give it a go, see what we come up with. So yeah, excuse the less than ideal filming of the laptop screen. I need to sort out a screen capture and microphone and stuff. So anyway, the circuit is as follows. So just disregard the ground symbol there. That's just so the simulator could run with something it demands a ground symbol. So that would be the mains coming in. So first things first, there's just an inrush current limiting resistor and a capacitive dropper, and that's just a discharge resistor for the capacitive dropper. Because the TRIAC is going to be referenced, it needs to be AC referenced on MT1. It's only halfway rectified. This part of the mains, this will be the whichever side I end up being, that'll probably be the neutral side. Actually, switching the line will then go through the load. So yes, this would be the neutral side. So it's halfway rectified, so it can create a negative voltage rail through this diode, and then the cap can then discharge, recharge, whichever way around you want to look at it, through this diode. So a simple dual Zener clamp, one single 12 volt would do, but it just separates the power dissipation between the two, makes it run a bit cooler. Smoothing, so that's the power supply side of it. It's dead simple. Control side, just imagine there's a TRIAC sat here with the gate at this point, main terminal 1 there and main terminal 2 going off to the load, which would be between this point and the TRIAC. So upon power up, this capacitor is discharged, and the only way for it to be charged up is through this 1 meg resistor. Oh, and it is charging. I know it's on the negative side, but it's still got 0 voltage across it until it charges through this resistor. And this comparator here has the non-inverting input being pulled up towards the upper rail through a voltage divider, which is keeping its non-inverting input at a higher potential than its inverting input. This capacitor is keeping this comparator's non-inverting input at a higher potential than its inverting input. This gives the circuit a few hundred milliseconds to stabilize till the power supply level has built up. Once the power supply breaks over about 8.2 volts or so, this Zener starts conducting. When it gets to about 12 volts, the voltage at this point becomes higher than the voltage at this point. This comparator goes low, starts charging this capacitor up through this resistor. The whole time that is going on, there is a portion of the main cycle which is going through this resistive divider here. So it comes in from the 1 meg resistor. These two diodes clamp it. It can never go above or below the voltage rails. And these two resistors here form a divider at AC, but they also offset it slightly towards the upper rail. The point being that this signal needs to rise above 0 slightly before the mains actually crosses 0 to ensure that the TRIAC is fired on both halves of the main cycle. So if you was to look at a positive going incursion, this resistor is taking the mains, dropping it down to just a few volts really. Once it gets above the lower rail voltage, this comparator output goes low, the SCR is fired through the 2K2 resistor. For the rest of that main cycle it conducts. On the negative going incursions, before the after the mains has crossed 0, this comparator still remains low enough for the TRIAC to fire again, so it will then conduct for the whole cycle. So that would be when the circuit is in full conduction, but there is an intermediate point. As this capacitor is charging, it creates a ramp. So depending on where the main cycle is, it only starts firing near the, to start off with it's on positive going incursions relative to this circuit's sense potential. So to start off with, it will only fire the TRIAC at the very peak of an upper incursion into the main cycle, and then this comparator is actually turned high again before the 0 crossing. So the entire lower portion of the waveform, there's no conduction. Then eventually it starts just ramping it up until you get just about 180 degrees conduction, and then all of a sudden you get full mains conduction. So it's not very linear, it's not overly gradual. It will sort of slam about. It's hard to do the maths because you just basically work more on power in terms of maths. It will slam about quarter power in to start off with, then ramp up to about half power over the course of a few seconds, then all of a sudden it will just switch over to the load getting full power, which is still a lot better than the high inrush it would normally get. It just allows the bulb a few seconds to warm up before full AC mains is applied. So yeah, that's the circuit. I'm actually missing a pass. There should be a small capacitor just across here and here to stop, because this is quite a noisy power supply, just to keep this voltage stable as well. I've missed that out of the schematic. So yeah, some things of note. This resistor will have full mains voltage across it, so I need to find something that's going to be able to handle that. Technically this resistor isn't strictly needed because there's always discharge pass through other parts of the circuit, but it's just good practice to have it there. And yes, that is the circuit, and so I need to go dig out some components and see what I can find. Right, so I've had a dig through my various many boxes of parts from old components. So I found a nice resistor for a bit of inrush limiting. I went with a 680 ohm. A small heatsink just to mount the TRIAC on, probably doesn't actually need it. The TRIAC is a TIC206D, and then yes, various resistors and capacitors and stuff. So yeah, and a small case to put it all in. Now I do have like a small metal case somewhere, but still don't actually have a proper setup around here yet to do work, and I've got stuff all over. So yes, I've been preoccupied doing things in this place rather than getting it ready to do things in this place. So unfortunately I'm still working off this small table with everything in boxes and bags. So I've just elected to use this small plastic box because firstly the wires come from the lamp are only a twin cord thing, so I don't have to then run a new cord and earth a metal box out. Secondly, this is a little bit bigger than the metal box I had, and it means everything can easily go in here without much messing about. Oh yeah, I've got a couple of dropper capacitors as well. But also, although I did find some perf board, first of all, it's not really best rated for mains potential. Admittedly, you know, I can leave plenty of spaces between any mains potential. But I can't, not for the life of me, find the small little handheld drill thing you use to just put the little holes in it. I have searched high and low and I can't find it, so I'm going to do this the good old-fashioned, possibly, see how I feel about it. I think I'm going to do this the good old-fashioned everything point to point like it's the 1950s and I'm making a television or a radio. See how that comes and works out for me. But yeah, then I can just have wire coming in, wire going out, and I've even got this little little switch, if I can squeeze it in here somehow. I do have a drill bit and a, oops, dropped down on the floor, and a step drill to drill some bits and bobs out. See, I can use this little power switch, should fit in there nicely, just about somehow. Once the lid's on there, might not be just enough room to squeeze it in. It would be close, I think is the word. So yeah, I'm going to knock this up, and fingers crossed it actually works. Yes, and if it does work, I might just fill it full of something, pot it somehow. Wax would be interesting because a few components will get warm enough to maybe just melt the wax around them, but most of them won't. So yeah, see what happens, I guess. Well, it's several hours later, and as you can see, this is I just knocked up a little somewhere around here. I just ended up wrapping some tape around a drill bit. Yes. So anyway, this is what I have in regards to the circuit. Lock you off there. So you see TRIAC is there as the input, the capacitive drop with current limiting, power supply is basically this side, and yeah, this is the timing thing. So does it work? That is the question. Well, technically yes. Made a few mistakes, had a solder bridge was causing some issues, and put a Zener diode in backwards. So it does this. So I don't know if the camera will pick up on that. I might film it again in a minute with a faster shutter rate and the not faster shutter rate, shutter angle cranked right down. So first of all, it takes too long to warm up, but secondly, you can very much see rectification artifacts from the diode, the TRIAC only conducting on half the mains waveform. Let me see if I come in on that. Maybe if I turn the shutter speed up. So you can see it takes quite a while, and then there's a little pulse for a second or two just as it kicks in fully. It seems to flicker a bit, and then it comes on. So I mean, it works, but I'm kind of thinking, let's get get you back to where you want to be. So I'm kind of thinking, if I were to say, for instance, this capacitor here is the one which determines how long it takes to come up to full speed. So I can either decrease the resistor that charges that cap, or I can decrease the cap. So I'll probably just So yeah, a few modifications later. So I've ended up dropping the timing resistor twice. It was originally 1 meg in series with 4.7 microfarads. I dropped it to 270k. It was still too slow. I've actually dropped it right down now to 51k. So basically 1/20th of the time I originally went with. And to do away with the annoying weird flickering thing, just went dead simple. Resistor. That's an 820 ohm resistor. It would overheat rapidly if it had full duty cycle, but however, because it's only momentary, it's more than capable of handling it. And also, it is only for about half a second or so before the TRIAC starts switching. So yeah, if I turn it on now, so you can see there's like 3 distinct stages. The first one, where it first comes on, is purely the resistor passing current. Then a few hundred milliseconds the TRIAC starts conducting, and then after about a second it goes into full conduction. So yeah, try that again. 1, 2, 3. So yes, there we go. So now I'm just going to bung it in this little plastic case. See, I'll put a bit of Captain tape around the TRIAC so it doesn't end up shorting against anything else on the board, because the tab is connected straight to MT2, I think. But yeah, so this is in the neutral side, or it will be in the neutral side of the circuit, so the live side goes through the lamp. But yes, there we go. Let's look at that in all its glory again. Just because we can. If I get the camera to let me focus. There we go. So it is still a little flickery when the TRIAC is in the intermediate state, but at least it definitely isn't pulsing current as bad as it was before, because the resistor is always going to let some current pass. I did actually try it, and I thought it would probably break the TRIAC, and it did. Instead of using a resistor, I just tried using a cap, and it would actually, interestingly, you could take the comparator out and the TRIAC would self-fire because of some phase shift thing going on between the power supply and the output waveform. And then of course every time the TRIAC switches, it's now trying to shunt capacitor, which it really won't like, and yeah, it did it for a second or two, and then it just went full short circuit. I didn't go full short circuit, it just wouldn't turn off after that. It had like some threshold thing where it would come on, and then after a second or two of sort of coming on, it would then just go into full conduction. But anyway, yeah. So all I'm going to do is literally put this in here and put the wires in each side where the switch used to be. Hiccups. And that'll do. So there it is, all back together. There was actually enough room in the base to just pull the base off it and put it all in the base, so didn't have to use the chunky blue box. So yeah, still using the original switch. If I turn it on, you can see there you go, it goes through its 3 cycles. Just do that again. There we are, works a treat. So is it necessary? No. Will it make the light bulbs last longer? Slightly. Was it just because I was bored and wanted something to do with the bag of TRIACs I've had in the cupboard for a year? Absolutely. So yes, anyway, any suggestions or comments or questions or anything else, feel free to drop a message, and if you've actually watched the video to this point, then thanks very much and catch you again.